Subhash Chandra Pan from IIT Guwahati. Here in this class, I usually try to solve some question based on this topic. Where I solve some questions based on this and which may help you to clear your doubts regarding this chapter, and also gives the initiative to solve some questions for upcoming examinations. So let's start. So the last few classes I was discussing about, initially I was started with the oxidation, then after finishing that one we focused on reduction. So in the last two classes we have already discussed about this lithium and sodium metal based reduction. Then in the last class we discussed about hydride donor based reduction. Today we will try to discuss more about this one, where how we can perform the reduction by using hydride donor in a asymmetric way or in a stereoselective way. Then we will focus on this hydrogen atom donor reduction. So in the last class we have discussed about the hydride donor reagents like LiLH4 and NaBH4 and how they react. There I have discussed about the mechanisms also. These are the very common reagents which has been used for reducing carbonyl groups like aldehyde, ketones, ester, and as well as acids. LiLH4 usually can be used for all of them. The LiLH4 is as strong, so it can reduce all the carbonyl groups like aldehyde, ketone, esters, and acid. If we use NaBH4, that selectively you reduce the more electrophilic group. That is, if there is any carbonyl, there are two carbonyl group like aldehyde and ketone. NaBH4 usually choose the aldehyde over ketone. That we know about all these things. And NaBH4 can't reduce ester that much, but LiLH4 can reduce the ester. There is another reducing agent called TAship that can be used for reducing one step. Like if we are using RiboH for ester, we can get aldehyde from ester. So we can do one step reduction by using RiboH. And specifically for acid, we usually use BH3 for reduction. That is very selective for acid. If there is a group, if any compound has two groups, like suppose there is an acid group and a ester group. All these things I have discussed in the last class. If you are interested, you can go and check. Still, for a recap, I am just giving. Now you want to selectively reduce this acid group. You want to selectively reduce this acid group. If you add LiLH4 in this, if you add LiLH4, the common reagent, if you add LiLH4 in this, both of the acid and ester group will be reduced to alcohol. But if you want to selectively reduce the acid group, what you will add? You will add BH3. If you add BH3, selectively the acid group will be reduced. Now if you similarly want to reduce this ester group selectively, you have to have a lower reducing agent than LiLH4, that will be Na. If you add LiLH4, both of them will be reduced. So just a slight weak reducing group you have to add. So instead of NaBH4, we can use LiBH4. NaBH4 is too weak to reduce ester group sometimes, so that if you use LiBH4, then it will reduce the ester group selectively. All this have been discussed in the last class. If you want to, if the slides have been uploaded also, you can go and check the questions from there. Okay, so this is a small recap how we can selectively use this hydride donor reagent for reducing different carbonyl groups. So how we can control the stereoselectivity of the product by using this hydride donor. So just by using different hydride donor, we can control the stereoselectivity of the reaction. Like what product will get if you are generating any chiral center. If you are generating any chiral center, suppose you have such kind of group. Suppose you have a R and there is R dash. Okay. Now just after reduction, what will happen? It will give a alcohol. After reduction, I am not drawing the reagent, just after reduction what will happen? It will give a alcohol. Now there are two probabilities, that which is above the plane another is which is below the plane. So you know what are they? These are enantiomers. These are enantiomers of each other. Now you have to, based on the nature of the reagent, one enantiomer will form in a greater amount and another enantiomer will form in a less amount. Like one will be major and another will be minor. That is called stereoselectivity. So here you can see, if you are taking this type of cyclohexanone group, you know this type of cyclohexanone. Now this in a cyclohexane there are two types of bond. One is axial, another is equatorial. If you have this type of cyclohexane, these straight bonds are called axial. This is axial, this is axial, this one is axial, this is from the behind carbon. This one is axial, this is axial, and again a bond here, this is axial. So all the carbons have two types of bond, one is axial, another is equatorial. So all these are called axial and these are called equatorial. These are equatorial. These are called equatorial. Okay. The blue bonds are equatorial and the red bonds are axial. Now if you have a cyclohexanone group, now the reducing agent will approach either from the axial or from the equatorial. So then from the nature of the reducing agent, the selectivity to approach the substrate changes. Like if you have if you know that whenever something is in axial, there is a strain called synaxial interaction with this axial bond. There is an interaction called synaxial interaction. So if something is approaching from the axial position, that group will suffer from a synaxial interaction. But if it is approaching from equatorial, there is no such called synaxial interaction. So if the group is highly sterically hindered, the reducing agent is highly sterically hindered or a bulky reducing agent, the axial attack will be unfavorable, because whenever it will try to approach from the axial, there will be huge steric hindrance between this axial hydrogen. Because of that, whenever there is a sterically hindered reducing group, the approach from the equatorial becomes in a major way, and we get this axial alcohol as a major. If the reagent approach from the equatorial, obviously this bond will open. If the hydride is approaching from the equatorial, this bond will open, this OH will go axial. Okay, don't get confused with the axial equatorial, because the reagent is approaching from the equatorial. That's why the newly generated alcohol bond will form axially. As it is coming from the equatorial, the newly generated bond will form axially. Okay, so as this attack is more favorable, this axial equatorial attack is more favorable. This equatorial attack is more favorable. That's why this axial alcohol forms in a major way, whereas this product form in a minor, because whenever it will try to approach from the axial, then it will feel a huge interaction. Because of that, this attack is less favorable and it is become a minor product. But if you have a less hindered reducing group, like the normal reducing group, like normal LiLH4 and NaBH4, in those case, because of the high stability of this intermediate state, the axial attack becomes major, and we get this equatorial alcohol as the major product. Just reverse of that one. If you have a normal reducing group, like reducing agent like LiLH4 and NaBH4, always the hydride group will approach from the axial. Like the straight bond, the hydrogen will form this straight bond, and product will be equatorial. But if it is a bulky reducing group, then it will approach from the equatorial and product will be axial. Okay. Now suppose substrate has also some control. This I was talking where substrate has no such group around the carbonyl group, then it has no such effect on the carbonyl group. So it's just simple, hydrogen is there and you are controlling from the synaxial interaction. Now suppose when the ketone is relatively hindered, then steric factor governs the stereoselectivity even over the small reducing agent. Suppose this type of group. Now in this case, this axial plane has this carbon, as there is a carbon center, so there are two hydrogen. Because of that, the axial attack becomes less favorable. Because of this two hydrogen atom, this attack becomes less favorable, and we get, this attack becomes, as there is only two hydrogen, so this attack can be from this equatorial position, because always, suppose you are consider this as a cave. Consider this as this type of cave. Okay. Now approaching to this kind of, you have to approach to this center. Okay. Now approaching to this center from this plane is more easier, or this one? For reagent. For reagent, obviously this one, because to approach from this side, you have to cover from, like across from this carbon, then you have to attack to this plane. So obviously this attack will be more favorable in case of this type of compound. So that's why the NaBH4 approaches in a major way from this side, and we get this axial alcohol as a major product. Now suppose there are two methyl groups. So in that case, if the hydride is trying to approach from this side, there will be huge steric hindrance between this group and this CH3 group. Because of that, this attack becomes less favorable, and to in that case, just to get a just to avoid this steric hindrance from this side, reagent will approach from the concave side. The reagent will approach from the concave side. So reagent will approach from this side. This becomes more favorable, not this one. That's why we are getting this equatorial alcohol. Don't get confused with equatorial axial. Just try to remember how the reagent will approach. Just attack. Then whatever product you are getting, just draw that one. Don't get confused that okay, this axial or equatorial. Remember, whenever that is a simple reducing agent and simple substrate, that will approach from the less hindered side. But if it is a bulky reagent or a bulky substrate, then the situation will be just reversed. Okay. So this type of substrate, there is a special case of this type. So try to remember this. Whenever there is a simple cyclohexane, the NaBH4 will approach from the axial. But whenever this type of ring is there, the attack is bit different. Try to remember when this type of substrate you get. So what is the stereoselectivity of hydride reduction? Just based on the substrate and the reagent. I have tried to show this by a chart. If the substrate is simple, substrate like this one, and you are adding NaBH4, this, in that case, you will get this percentage of endo alcohol, like the highest percentage of endo alcohol. But if we just change the nature of the reducing agent, this is a bulky reagent. In that case, the actual percentage increases. If you enhance the bulkiness of the reducing agent, it can goes to the greater than 99%. Okay. So there are some questions. Let's solve together. So reduction of other functional groups by using this hydride donor. So we know that hydride donor is used for reducing carbonyl groups. This can be used for reducing some other functional groups also. Suppose there is a given epoxide group. Now we are adding LiLH4. What will happen? We already said LiLH4 approach from the axial is more favorable. So it will approach from this plane and we will get . So this is the SN2 type of water. This will open. It will go. Okay. Next is this one. If you have this type of halide group, what will happen? Simple SN2 substitution. So H minus will attack at this place. And you will get just substituted product. Just a substituted halide will be substituted by the hydrogen atom. Next is, if you are giving this type of bromobenzene and add LiLH4, it can substitute this bromide from the system also. And you will get simple naphthalene. If you have this type of triple bond, LiLH4, reduction for triple bond always give a trans product. LILH for reduction of triple bond always give a trans product. Always give a trans alkene. Always give a trans alkene. Okay, so this is trans. Next is if you add LiLH4 in this type of substrate, this carbonyl will be reduced normally as we usually see. So, along with that, this sulfonyl group will be substituted and we will get this hydrogenated product. Okay. This is a OTS group. This is a OTS group, tosyl group, kind of. No, sorry, OMS group. This is a mesithyl group, OMS group. So this it will just H minus will attack here, and there is a bond. This bond will just get removed from the system. Okay. Let's go to the next topic. So hydrogen atom donor. How we can use hydrogen atom donor for reduction? Till now we have used metal and hydrogen gas. We have also used normal metal. Then we used hydride donor. Now how we can use hydrogen atom donor? So this type of reduction usually involves free radical intermediate, and you can use this type of reducing agent like one of the important reducing agent of this type is this tertiary tributyl tin hydride. So if we add to a halide hydrocarbon, it can be substituted and this CH bond will form. This is the order of halide transformation. With the increasing the bond strength between the carbon halogen bond, the rate of the reduction decreases. So as the carbon fluorine bond is formed due to 2p2p overlap, so it is more stronger bond than that of the other carbon halogen bonds. Because of that, to break this bond we need a higher amount of energy, so and the reaction becomes lower, whereas the RI bond, carbon iodine bond forms, bonds are comparatively weaker. Because of that, these bonds can be broken very easily by using this type of hydrogen atom donor. So this is the mechanism. If you have to need an initiator. Usually for this type of reagent we use AIBN as an initiator. We usually use this AIBN as an initiator. This is AIBN. This is AIBN. So if you just, this comes here, through homolytic cleavage it forms this, through elimination of N2 gas it forms this initiator CO2 dot. So this initiator reacts with this BU3SNH and it take up a proton from this BU3SNH and forms this radical. After that, this tin radical will attack to this, will take this halide from this halocarbon, then it will generate this R dot, then R dot will take a proton from another molecule of BU3SNH and form this hydrated product, and again this BU3SNH regenerated, which continues the cycle and react with another alkyl halide. So you just, to initiate the reaction you just need one mole of initiator. To react, just to initiate the reaction you need just 1 mole of initiator. After that the BU3SN dot will regenerate after each step and it will continue the reaction mechanism. Okay, so you just need 1 molecule of this initiator. So there are some questions based on that. Let's solve together. As we said, it breaks the halide bonds, so it will selectively breaks the carbon halide bond. It will not react with the carbonyl group. If you search this kind of group, this carbonyl group will be intact, whereas one of the Cl bond will be eliminated or substituted by a CH bond. Next is this one. Now there are 2 types of carbon halogen bond. One is CCl, another is carbon fluorine. So whenever there is a 2 carbon halogen bond, there will be a selectivity among these two, between these two, which bond will be broken by BU3SNH. Now we have already told about the rate of the hydrogenation. As much the bond strength of the carbon halogen bond increases, the rate of the reaction gets lower. So if between carbon chlorine and carbon fluorine bond, which bond is weaker? Obviously this carbon fluorine bond. So that when you are adding this hydrogen atom donor, what will happen? This carbon fluorine bond will break and carbon fluorine bond will be still there. So there is selectivity. Next is this one. Now you have to notice they have used BU3SND instead of H. So obviously when this steps happens, so there is, instead of BU3SNH, BU3SND is there, so R dot will take deuterium instead of hydrogen. So as a product of this one we'll get this deuterated product. So next topic, so reduction is almost, I have tried to cover whatever is more or less important for examination purpose. If in the upcoming classes, if I get some questions which include some important topics rather than whatever I have discussed, I will try to include those. Till now, whatever I discuss about the oxidation and reduction, more or less the questions from NET or GATE comes around that. So There are some other topics also for reduction and oxidation, but those are not that much been included as a question for competitive exam. So I haven't included that, but for further during solving some previous year questions or whenever I will get any important type of reagent which I haven't discussed yet, I will try to include them in the upcoming slides. So today the next topic we will discuss about the reagents containing silicon. Silicon in organic chemistry. The main difference from carbon, nitrogen and oxygen is that silicon. So we will discuss about silicon, phosphorus and sulfur. Today we will discuss about silicon and sulfur. Next day we will discuss about reagents containing phosphorus. So these are very important organic reagents. So they are non-metal. First of all, they are non-metal, so they are not that much harmful for the nature. So that's why they are called organic reagents. And as the bonds are formed, as the silicon, phosphorus and sulfur can form more bonds than the first row elements, these have some vacant d orbital. Because of that, it can enhance this octet, and it can, so because of the ability to enhance this octet, it can show some different activity rather than oxygen, carbon and nitrogen atom. So you know, silicon belongs to the carbon group, phosphorus belongs to the nitrogen group, and sulfur belongs to the oxygen group. But they are in first row, but they are in second row. Because of that, they have a vacant d orbital, which helps them to enhance their octet, and it can form more bond than usually this form. Like carbon can form, how much bond carbon can form? Carbon can form 4 bonds. Carbon can form 4 bonds. Nitrogen can form 3 bonds. Remember about ammonia. Nitrogen can form 3 bonds, and oxygen, remember of water. So oxygen can form 2 bonds. Whereas these 3 atoms can form more than this. Silicon can form 5 bonds. Phosphorus can also form 5 bonds, 4 or 5 bonds. Sulfur can also form 4 bonds. So they can form more bonds. Because of that, it can get attached with different molecule and show some different reactivity. So silicon forms tetrahedrosilane rather than alkane, but also it can form 4 bonds, but also it can form a 5-valent anions. So it can react with another anion or another group and form this type of pentavalent complex. So if you want, we can perform substitution like similar to the carbon. The reactivity is quite similar to the carbon, but there are some differences which we will discuss. Like carbon have a leaving group. What happens if you are having a nucleophile? It will attack here. It gets removed and will form this carbon nucleophile bond. Okay, this is called SN2. Another possibility is leaving group just leave from the system. We get a carbon plus. After the nucleophile enters, and we get this product. This is SN1. But in case of silicon, the mechanism is bit different. In case of silicon, the mechanism is bit different. The most effective nucleophile for silicon are electronegative ones that will form a strong bond to the silicon. Those based on oxygen and halide, usually oxygen and halide forms a strong bond with silicon. So if this mechanism is not a simple SN2 process and has direct analog in carbon chemistry, what will happen in case of carbon chemistry? This SN2 will but in case of silicon chemistry, what will happen? This nucleophile will attack to this silicon it get incorporated and form this intermediate, pentavalent intermediate, and form this type of, after removal of this leaving group, it form this type of tetracoordinated compound. So it is similar to the SN2 for carbon, but in case of SN2 for carbon we get a pentavalent transition state, but here we are getting pentavalent intermediate. So you know the difference between transition state and intermediate. Transition state is a hypothetical, wherever you show the bonds with like a dotted bonds like this. We are showing our bonds like dotted bond, like this type of. This is called transition state, and they are always shown in a third bracket. So this is imaginary. This is a imaginary complex. There is no such. These complexes can't be isolated or trapped. Okay, this is an imaginary complex. This is called transition. So they are always shown in a third bracket with a dagger sign. So they are called transition state. But in case of silicon, we get an intermediate. So intermediates can be trapped by using mass or by using some another cationic species. You can trap this anionic species, or by if you inject this compound in mass spectrometry, you may detect this formation of this intermediate. So these are called. So this is the difference for silicon chemistry. So there are, using this silicon chemistry, there are two types of olefination reaction, like the double bond forming reaction. So Peterson reaction is stereospecific. In principle, this is an M reaction. In principle, it can therefore be used to make single geometric isomer of alkene, and the geometry will depend on the relative stereochemistry of the certain material. So this Peterson olefination can be performed in a two way. One is acid catalysis, another is base catalysis. So acid catalysis reaction usually go through an anti-elimination, and base catalysis reaction go through a syn elimination. You know about elimination reaction. If you have a hydrogen here and a leaving group here, if the removal is like this way, and forms a double bond, this is called anti-elimination. And if you have a hydrogen atom here and a leaving group here, and reaction is performing like this way. This is called syn elimination. So this is called anti-elimination, this is called syn elimination. So Peterson olefination can be performed in both ways, depending on the catalyst you are using. If the reaction is acid catalyst, it will be anti-elimination. If it is base catalyst, it will be syn elimination. So let's check the mechanism. E2 elimination proceeding via an anti-peripheral transition state. So in case of acid catalyst, what happens so this is the substrate for Peterson olefination. You should have a silicon substituent in just beside your leaving group. Here you have a OH. So OH is a bad leaving group. So if you have adding acid, then OH become OH2 plus. OH become OH2 plus. OH become OH2 plus. So they are already in the opposite plane, as they are shown in a dotted and above. They are already in opposite plane. So silicon will come here and this gets removed, and we will get this anti-product. Now suppose you have both the group in the same plane of the substrate. Both are below the plane, and you are performing an acid catalyzed Peterson olefination. That is not possible because leaving group and the eliminating silicon group should be anti-peripheral to each other. So that's why you will just rotate this bond. You just have to rotate this bond so that the stereochemistry of this one changes. After rotating this one, the silicon will be same as we have rotated this portion. The silicon will be same, but OH will go above the plane. So now they are in the opposite plane. And if we add acid catalyst after that, this is, don't get confused with scene elimination with this one. Just see, in this case I have shown these two bonds in a normal planar bond. That's why we have to show this in a different way. But in this case you can see this OH is above the plane, silicon is below. They are already anti. They are already anti to each other. Just imagine this in 3D. This OH is above the plane and silicon is below the plane. So they are already anti. So whenever we are showing this as they are on paper, so it seems like this is a scene elimination, but it's not, because both are in the different plane and this is anti-elimination. We get this as a product. But in case of base catalyzed reaction, the mechanism is bit different. By addition of base, this O- will form. This O- will form. So this OH will and then O- will form, and now these two are in same plane. So we have this, for base catalyzed reaction both have to be in same plane. So we will just rotate this. Now both are in same plane. And after the formation of this cyclobutane ring, it will give us this as our product. Okay. Now let's solve a question based on that previous year. So what will be the stereochemistry of the product? The stereoisomers of G giving the depicted product. So what should be the, they have shown these two bonds in a wavy line. Wavy lines mean it can be above and below. It can be above or below. So they want the exact stereochemistry of this one to get this as our product. So the product is seen, but the substrate is anti. Okay, so that means this bond has been rotated. This bond has been rotated. Okay, you can understand that these bulky groups are anti to each other, but here there is seen. So during the means of the reaction, these bonds have been rotated. Now if you perform the reaction how they were, like if both are, like this is above the plane and this is below the plane, and as it is basic acid catalyst, BF3 is a Lewis acid, BF3OH2 is a Lewis acid, so it is a acid catalyst reaction. So if it is acid catalyst, that means it should be a anti-elimination. This should be a anti-elimination. So after rotating this group, both the silicon and oxygen should be anti to each other. So if you want to rotate this like this way, after this rotation, the silicon and OH should be anti to each other. That means if silicon is above the plane, then OH will be below the plane. So this is after rotation. Now we have to show this like this way. These two groups should be anti. So before rotation, what was that? So before rotation, So it was like that. So before rotation, what will be the possibility? As this bond has been rotated. After rotation, this OH is going to the below. That means before rotation, the OH was above the plane. Okay, you are understanding, right? As the after rotation, we are getting this OH in the below. That means before rotation was OH was above the plane. So if you want to draw this one, what will happen? It should be like, I am just showing this as a R, this one as a R, and this is R dash. So if they are anti and silicon is above the plane, so before rotation the hydroxy group was also above the plane, as after rotation it's getting this, is going to the below the plane. So which is matching with this option A. Option A. Okay. Let's go to the next question. So next topic. So I have already told we will discuss about silicon and sulfur today. Next class we will discuss about phosphorus, and phosphorus is quite broad than these two. So sulfur is another reagent. Sulfur can have any coordination number from 0 to 7, forming sulfide like ethers, tetrahydrosulfone with 6 bonds to sulfur. Thiols are more acidic than alcohol, but sulfur compounds are better nucleophile than oxygen compounds towards saturated hydrocarbon. Sulfurs are better nucleophile. Why? Because if you have the sulfur has less electronegativity, so it has more probability to give its electron to a compound, so it has a better nucleophile than that of other saturated carbon atoms. Sulfur in organic sulfone stabilized carbon ions have 2 oxygen atoms and the anion carbon atom is probably planar. Sulfide functional group also acidifies the adjacent proton quite significantly. So if there is a adjacent proton is there, because of the high electronegativity effect and also after elimination of this proton, this negative can be dispersed to this vacant d orbital of sulfur. Because of that, the acidity of this adjacent proton enhances and becomes highly acidic. The positive charge carried by the sulfur atom means that proton next to the sulfur atom is in a sulfonium salt and are also significantly more acidic than those sulfide. If the sulfide is positively charged, this hydrogen becomes more acidic and we can take up this proton very easily, and sulfonium salt can be deprotonated to give sulfonium ylide. Sulfonium ylide react with the carbonyl compound like this way. O minus will be, then O minus will attack again to this carbon center and sulfur will be eliminated and form this epoxide as our product. During discussing the epoxide, I have already told that sulfonium ylide can also be used for epoxide. We have already discussed about this a bit. So substrates which are, you know that MCPB are bit acidic, and for MCPB reduction, this double bond should be MCPB epoxidation. The double bond should be electronically rich, and for H22 that should be electronically deficient. But for simple, if you want to form epoxide from a carbonyl group, that is from double bond. MCPB epoxidation MCPB epoxidation is forming epoxide from a double bond. Now if you want to form epoxide from a carbonyl, in that case you have to use sulfonium ylide and you will get this type of epoxide. So instead of, so there are two types of sulfonium ylide. One is simple sulfonilamide or one is stabilized sulfonilamide. Stabilized means if there is an electron withdrawing group adjacent to the sulfonilamide, this O minus can be stabilized by this electronegative group. So that's why it is called stabilized sulfurylide, and the next one is unstabilized. So whenever on a alpha beta unsaturated double bond, if you are adding unstabilized sulfonilamide, it will react with the carbonyl group and give the epoxide. But if you add a stabilized sulfonilamide to this alpha beta unsaturated group, what will happen? It will selectively react with this alpha beta unsaturated double bond and give us this cyclopropane as our product. There is another important type of sulfonilamide is called sulfoxonilamide. This is equivalent to this stabilized sulfurylide and also give the same reactivity like the stabilized sulfurylide. Sulfoxonilamide is equivalent to stable sulfonilamide. So it will react in the similar way. If you are adding any alpha beta unsaturated aldehyde or ketone, it will selectively react with the alpha beta unsaturated double bond. But if you are adding unstabilized sulfurylide to alpha beta unsaturated double bond, it will react with the carbonyl group. So there is a question: what will be the major product P and Q formed in the following reaction? So in this one they have given a sulfonilamide, another one is this is a sulfonilamide, and this is a sulfoxonilamide. We have already told if we are giving a sulfonilamide, what will react? The carbonyl group will react. So this group will react. So we will get a epoxide. Whereas if you give a sulfoxonilamide, this double bond will react alpha. So correct option is this one. Sulfonilamide will react with this part, whereas sulfoxonilamide will react with this part. Okay. So let's solve some previous year questions one by one. Here I have tried to include whatever, if I have missed any questions based on reduction and oxidation, I have included those one also. So let's solve one by one. So addition of BH3 to a carbon-carbon double bond is anti-Markovnikov scene addition, anti-Markovnikov anti-addition, Markovnikov scene addition, or Markovnikov anti-addition. So here I have included the Markovnikov rule. What is Markovnikov rule? When an unsymmetrical reagent added to an unsymmetrical alkene, the negative part of the reagent adds to the sp2 carbon that is bonded to a less number of hydrogen. Suppose we have this type of group. So if you add BH3, what will happen? The hydrogen goes here. The BH2 goes here. So that means the carbon having less number of hydrogen getting the hydrogen. That is called Markovnikov rule. So obviously this is following the Markovnikov rule, and the addition is scene addition. The answer will be option C. Okay. Next is this one. If styrene is react with liquid lithium and liquid ammonia, what will happen? So this is styrene. So the alkene double bond, we can consider this as a electron donating group. After addition of this product, you will get this as our product. As lithium is still in the medium, this goes here. We will get this as our product. So the correct option is option D. Okay. This is one of the important questions because this sometimes we stops here and we take the question, but reaction will not stop here. It will go through this type of conjugation to get more substituted double bond, and we will get this as our product. The major product formed in the following reaction sequence. So first step, some of you may know, some of you not. Maybe I haven't discussed yet. This is called Baeyer-Villiger oxidation. This is called Baeyer-Villiger oxidation. Whenever you have this type of peroxide, this goes through a Baeyer-Villiger oxidation. In case of Baeyer-Villiger oxidation, if you are adding this reagent to a carbonyl compound, what will happen? There is an oxygen incorporation between the more substituted group. So after this one, you will get a ester group. To form a ester from ketone, this is a very important type of reagent. It will form this ester group. After that, LiLH4 reduction. This H minus will attack here, and this will open. Form this aldehyde and alcohol. Again, this aldehyde will get reduced. And form alcohol. Now as both are below the plane, so the correct option will be option B. Okay, so correct option is option B. The major product formed in the following reaction sequence. The reagent contains a silicon and we are adding base. So this is a Peterson olefination. This is a Peterson olefination. Now which type of Peterson olefination? This is a base catalyzed Peterson olefination. So what, there will be a syn elimination. There will be a syn elimination. So between two OH group, which one is syn to SiMa3? Obviously this one. So there you have to be selective. If it is any acid is given, you will choose this one. But as any base is given, you have to choose this OH group. As this is a ring structure, the bond rotation is not possible. So after elimination, it will give form this O minus. It will attack here. After then it will get eliminated. Okay. After if you are adding MCPP, this will form a epoxide. This will form a epoxide. Now as OH group is already below the plane, so OH group, the epoxide will approach from the below the plane. So the hydrogen will be above the plane, so the correct option will be option B. As OH is below the plane, so the MCPP will approach from the below the plane, so the epoxide will form. At the below the plane. These two hydrogen here will be above the plane. So the correct option will be option B. Let's go to the next question. So now we have this type of cyclohexanone group and allylase for added. So it is a simple reagent and this is a simple substrate. There is no such bulkiness here. So it will approach from the axial center and we will get a equatorial alcohol. Next is this one. If you have this epoxide, I have already told epoxide, in case of epoxide, this H minus will attack to this A cinder center and this will open. It will form a OH here and H. Okay. Let's go to the next question. So they have if they have given this substrate along with the aldehyde and they added LHMD. This is a base. This is a base. This is a base. Now this what will happen? There is a proton. This proton is highly acidic. A proton adjacent to the sulfur is highly acidic because of this stability of the carbon ion through this vacant d orbital. We have already said. So this base will take this proton and it comes here. It will generate this. If I show this as AR. So this will attack again to this aldehyde center and form that, form this type of product. Okay. Next is the major product formed in the following reaction. So from this reagent you can see this is a hydrogen atom donor, so reaction will go through a radical pathway. So first it will form this SN dot radical, then that will attack again to this R and form a R dot. So after all the reaction it will form this type of structure. It will form this R dot. Now because of this ester group, this carbon bond is quite weak because it can be easily opened. So this comes here and attacks, and so it's just similar to the SN2 type of reaction. This opens. And form this carbon bond. Where there is a radical generated here. After that, it will take a proton from another molecule of Bu3SNH. And we will get A as our product. Okay, I hope it's clear. So this is almost end of this today's class. So the reaction that yield 3-phenyl cyclopentanone as the major product, among which of the reaction will form 3-phenyl cyclopentanone. So I am giving this as a homework because there are some reaction which I haven't discussed yet. So if anyone of you know about this, you can go and try by yourself. In the next class we will solve all these questions. So this is the last question of today. So I have already discussed about immunity oxidation in my first class or second class, I think. If you want to know in detail, you can go and check there. So from just for a recap, I say immunity usually selectively oxidize the allylic alcohol. Selectively oxidize the allylic alcohol. So this allylic alcohol will be oxidized to give this aldehyde. After that, this OH will attack to this aldehyde group and this will open. Now this is still a allyl alcohol. This is a still a allylic alcohol. So it will again oxidize. It will again oxidize and form this type of ester. So the correct option will be option 3. Okay, I hope you have understood. So this much for today's class. We'll discuss the other topics in the next class. So this is I just gave an overview. Today I discussed about stereoselectivity of hydride reduction, followed by some examples. Then we discuss about hydrogen atom donor and some examples of that. Then we discuss about silicon chemistry, Peterson olefination and examples based on that. Then sulfur chemistry and followed by its application. Then we solve some questions. So I hope you have enjoyed. We'll meet in the next class, and there I will discuss about more questions, interesting topics based on reagents in organic synthesis. So thank you. Have a nice day.